4 o'clock sharp, and then we'll start. Okay, let me get my ducks in a row. Okay, so Ludvig, have you got the slides up already?
Yeah, and I just put a link on my website to the streaming thing as well.
Okay. Actually, can we put the slides on the chat, maybe?
Yeah, sure. I'll put a link because there's a link to on my website to the slides, actually.
Okay.
It's all there. Let's see. Here. So I'll put it in the chat. There.
By the way, if you go to, I already told Ludvig, if you go to his webpage, you should download his mechanism design slides. They're very nice. Thanks, Ludvig. Okay. Should we? Yeah, it's exactly 4 o'clock according to my clock. So I'm going to start the introduction. Welcome everybody to VSET, a new season. We start today with Ludvig Sinander from Oxford. He's going to talk to us about the comparative statics of persuasion. This is joint work with Gregorio Curello, who's also with us, and he's going to answer questions in the chat if you have a clarification question. Ludvig is happy to take questions if you feel like you need to ask directly, and in that case, you can just unmute yourselves. We also have guest panelists, Philipp, Strack, and Itai Arieli, who we thank very much for being here. And just a reminder, on the 13th of October, next week, we have Eduardo Perez Richer from Sciences Po. He's going to talk about fraud-proof non-market allocation mechanisms. And maybe some of you know, some of you don't know, on December 1st, we're going to have, I just wanted to advertise this, a joint venture with Women in Economic Theory conference. And the best paper that they feel, the person who they feel has the best paper is going to present on December 1st here at VSET. Okay. So, and as usual, we'll stay a little bit longer after the end of this, 60 minutes plus 15 minutes for questions. Ludvig, the floor is yours.
Thanks very much. Thank you for having me, and thank you all for coming. As advertised, this is joint work with Gregorio, who's here in the chat, and also with a video link. So here's a picture of Gregorio, actually, which is unnecessary for this talk. Okay, so this is still pretty early work. So we put a preliminary version of this paper online a few months ago, but we haven't worked on it since. So it remains preliminary, which means that comments are genuinely very welcome. Okay, so this is a paper about the persuasion model, which has received a great deal of attention in the last 10 years. The question in particular that's received a lot of attention in the persuasion model is what optimal signals look like. Okay. It turns out to be a reasonably hard question. So there's a number of very interesting papers about this. Here's some sort of selection. So there's some of these papers that obtain high-level insights at a pretty high level of generality, and some which obtain sharp characterizations at the cost of having to make strong assumptions. Okay. All very nice. Okay. But these questions all ask one of the questions that these papers all ask one of the questions you can ask of an economic model, which is, given the primitives, what do optima or equilibria look like? Okay. There's another question that we ask of economic models, which is, if the primitives change, how do the optima or equilibria change? So the comparative statics question. And that question has been open for the persuasion model. And what we do in this paper is to answer it. Okay. That's that simple, I guess. So let me give you one slide's worth of overview of what that entails, and then I'll give you the contents of the paper. Okay. So we take as our primitive in this paper the sender's payoff at the interim stage as a function of the mean of the posterior distribution. Okay. Now, our question is going to be, what shifts of this object lead the sender optimally to choose a more informative signal? As many of you know, though, more informative than is a lot to ask. Okay, this is a very incomplete partial order. Okay. So we find it useful to break our question down into two sub-questions. Okay? We start with the easier question of what it takes to get non-decreasing comparative statics. What shifts of the primitive lead the sender optimally to choose a no less informative signal? Okay, so her signal could become more informative, or it could shift in such a way that it becomes neither more nor less informative. It's just different information is provided. Now, the answer to that question is, intuitively enough, to do with convexity of the sender's interim payoff, if and only if the sender becomes more convex in a suitably defined sense, she's going to provide no less information. That's our first theorem. Now, that tells us that if we want increasing comparative statics, we want more information to be provided, it is necessary that the sender's interim payoff become more convex in this appropriate sense, but that's not sufficient. Okay. So what we do in the remainder of the paper is to find the property that fills the gap, that ensures that the pathology of an increase of convexity failing to lead to increased information provision does not arise. Okay. So that necessary and sufficient condition, in other words, ensures that under that condition, coarse convexity shifts lead to greater information provision, and without that condition, they may not. Okay. I'm going to tell you in due course what that condition is. What I'll say about it now is just that a special case of this condition is that the sender's interim payoff have an S sort of shape. And I mention that because the S shape plays a pretty big role in the existing literature on the persuasion model. And in fact, there's a just published TE paper by Anton, Tima, and Andri, which obtains comparative statics for this S-shaped special case. Okay, so our theorem nests theirs, which is nice. But they got there first. Okay, so that's all the introduction I have. So unless there are questions, I'm going to tell you what the persuasion model is, although you probably already know. I put my hair up when it gets serious.
I think we can go ahead, sounds like.
Good. Okay, so here's the model. Okay. In this talk, I'm going to use the word distribution to mean a CDF defined on the unit interval. The model is like this. There is an uncertain state of the world, which is what? It's a bounded random variable. Okay. I might as well normalize the bounds to be 0 and 1 because I'm that kind of person. Okay. Now, the distribution of this random variable, I'm going to call it the prior. Sometimes I'm going to call it F0. Okay. The distribution of the state. Now, the model features one character whose name is the sender. And what the sender does is to choose a signal. And a signal is nothing more or less than another random variable defined on the same probability space. So it can be jointly distributed with a state in whatever way the sender wishes. Now, the state's not going to be observed, but the realization of the signal is. Okay. So given the prior, and given a choice of signal by the sender and a realization of that signal, Bayes' rule prescribes an updated posterior belief about the state following the observation of the realization of the signal. Okay. And that distribution, that posterior distribution, has some mean, and I'm going to call that the posterior mean. Posterior mean just means the mean of the posterior distribution. Okay. That's what's going to matter. Now, since the realization of a signal is random, that means that if I just think about a prior and a signal, well, they induce a random posterior mean. Okay, that's another random variable. Okay, so every signal given the prior leads to some random posterior mean. And the assumption is that the mean of the posterior distribution is all that matters to the sender. Okay, she has some payoff function, little u, such that at the interim stage, if the mean of the posterior distribution is m, then her payoff is u of m. Okay. So at the ex-ante stage, at which the sender chooses among signals, she's an expected utility maximizer. So she chooses among signals so as to maximize the expectation of her interim payoff, given that every signal induces a random posterior mean. And by the way, there is a more general version of the persuasion model in which the whole distribution can matter, the whole posterior distribution, and not just its mean. I'm not going to have much to say about that today, but maybe we will in the future. That's the model. You may be wondering where the receiver went, so I'm going to mention her only to put her back in the box for the rest of the talk. Okay. A micro foundation for the model that I just described features a second player called the receiver. Okay. There's a set of actions in this micro foundation over which both the sender and receiver have preferences, which can depend on what their posterior mean happens to be. Okay. Now, the receiver is the one who's in charge of action taking. So she has a prior, observes the realization of the signal chosen by the sender, updates her belief, and then chooses an action. She chooses an action in her own interest. In that case, what is the sender's payoff as a function of the posterior mean? Well, it's just her payoff when the posterior mean is such and such, and the action taken is the action that the receiver likes to take at such and such a posterior mean. So that's the usual way, from the usual foundation from which this reduced form payoff of the sender is derived. Okay. But as I said, for the purposes of today, I'm going to be treating this payoff defined directly on posterior means as a primitive. That's what I'm going to be looking for conditions on. Okay. And then there are a number of homework exercises, which we haven't done yet, to the effect, what kinds of shifts of the primitives in the sender-receiver story lead to the shifts that turn out to be appropriate for the sender's interim payoff defined directly on posterior means. Okay. So that's not today.
And if I think of more informative signals as meaning that the receiver is better off, couldn't I also think of the question just when is the receiver better off?
Yes, that's a good point.
Or is that equivalent?
It's not equivalent because we only, we have one receiver at a time. And the notion of more informative than that we're going to be working with is, in the spirit of Blackwell, going to be equivalent to every conceivable receiver is better off. But the problem is that the sender is going to change what information she provides depending on what receiver she's facing. So they're not equivalent. And your question is a very natural one, which is just not the question we're asking. Maybe we should answer that question as well, though. I think it's a good point.
I guess you can always think of it as such when you take the receiver to have a kind of a responsive best reply that changes one-to-one with the belief, and in such a case with the mean, in such a case you can take the U with respect to the same receiver, right? So I guess if you look at it like that, you can think of the receiver as fixed.
I think that's true, but that implicitly corresponds to a restricted class of receivers, which would correspond to a less demanding notion of comparative informativeness than the one we're going to be working with. So that would be natural, but it's not. I don't think that is equivalent to the question we're asking here, actually.
Do we know conditions under which A star of M is unique?
Yeah.
Okay.
Yeah, I'm sure we do. It doesn't actually matter for the purposes of the micro foundation, though, because A star can just be any selection, and given whatever selection you think is the most plausible, that's the one you plug in to obtain UM.
Thanks.
Yeah, thanks. So thanks for all the questions. Okay, so now we're going to put the receiver back in the box, and she's not going to come back out. Okay. So the way I formulated the model, the sender chooses a random variable, a signal, which is a pretty nasty problem. Okay, so here's the usual reformulation, which is due to Anton, of the problem, which is more tractable. Okay. Recall that one distribution is called a mean preserving contraction. A mean preserving contraction of another if the area under the contracted distribution between, integrating from 0 up to some x is always smaller than of the more spread out distribution. Except if you integrate all the way up, you get the same answer for both distributions. The areas under the two CDFs in total are the same. The condition of equality when you integrate all the way up to 1, upon integration by parts, becomes equivalent to these two distributions having the same mean. Okay, so that's the mean preserving part, and then the inequality of the areas up until there, that's the contraction part, if you like. Okay, so here's a fact which is useful and which is variously attributed to Strassen or Blackwell or somebody. Okay, it's the following: for a distribution f, there exists some signal whose induced random posterior mean has this very distribution f. Exactly if this distribution f is a mean preserving contraction of the prior. Okay, so if we think not about signals or the random posterior means, the random variables, but just about which distributions of random posterior means can be induced by choosing some signal, that set of distributions that are feasible turns out to be exactly the set of mean preserving contractions of the prior. Okay, this is a standard result. Okay, the extreme cases, to build some intuition, are one mean preserving contraction of the prior is the prior itself. Well, that's obtained via a fully informative signal. Okay, a fully informative signal leads to almost surely at the interim stage, the belief assigns probability 1 to the true state. So the mean of the posterior distribution is equal to the true state, almost surely. Right? So that means that the posterior mean has the same distribution as the state. Okay. And the other extreme case is where the distribution in question f is just the point mass at the prior mean, at the mean of the prior distribution. Okay, that's a fully contracted version of the prior. Okay, that's obtained with a fully uninformative signal. Okay, with a fully uninformative signal, almost surely at the interim stage, the belief, the posterior belief, is exactly equal to the prior belief. And so almost surely the posterior mean is equal to the prior mean. Okay. What the result says is that you can get anything in between. Okay. So that's useful because in that case, we can reformulate the sender's problem as choosing among the mean preserving contractions so as to maximize the expectation still of the function u. And this is now a linear maximization problem with a constraint set that is not too ugly. Okay, this is not inside, these insights are not due to me, to be clear. Okay, so to talk about comparative statics, to talk about informativeness, I need to define comparative informativeness. And so here's my notion. One distribution is less informative than another exactly if it ascribes a weakly lower expected value to every convex function. So as I alluded to just a few moments ago in response to a question, this is an informativeness notion in the spirit of Blackwell. Okay, if we think about all possible decision makers who care only about the posterior mean and have to choose among some set of actions, okay, what this says is exactly that all such decision makers prefer to have information such that their distribution of posterior means is G, the more informative distribution, rather than to have a signal which gives them posterior mean distribution F, the less informative distribution. Okay, that's because all and only convex functions can be arbitrarily well approximated by value functions of such decision problems.
We're talking about distributions of means, right?
That's right. That's right. Yeah, thanks for asking. Yeah, incidentally, I mean, for me at least, when I started looking at this linear version of the persuasion model, it was a little confusing because here we're contracting instead of spreading. So I don't know if that's... Okay. That's the informativeness notion. And now something I have to mention, because it would be confusing for some of you if I didn't, is that actually informativeness and mean preserving contraction are equivalent. This is well known. Okay, a distribution is less informative than another exactly if it's a mean preserving contraction. Okay? So which means that I can write the constraint set in the Sender's problem as choosing from all the distributions that are less informative than the prior. And so I think this is the way I've written it in the subsequent slides, actually, as it happens. Okay, so one more piece. In principle, there might be multiple optimal distributions, which means that in order to talk about comparative statics, I have to compare sets of distributions in general. So I'm going to do that in a standard fashion using what's called the weak set order. In particular, I'm going to say for two sets of distributions that the one is lower than the other, exactly if for any distribution in the lower set, I can find some more informative distribution in the higher set. And dually, for any distribution in the higher set, I may find some lower distribution in the, some less informative distribution in the lower set. I don't know if I just said higher and lower instead of informative, less or more informative. If I did, I apologize. Okay. The really key property of this set order is that if I'm comparing two singleton sets of distributions, so that's the case in which the argmaxes are singletons, so there's just one unique optimal distribution, right? This just boils down to the distribution in S is lower than the distribution in, well, so then S is lower than S prime exactly if the single distribution in S is less informative than the single distribution in S prime. By the way, so it turns out that nothing is lost if you imagine all the argmaxes being singletons for the whole rest of the talk. So feel free to do that, actually. Okay, and then just to avoid complaints, I'm going to define higher as well. Okay, so one set is higher than another if the other is lower than the one. And by strictly lower, I'm going to mean lower and not higher. That was all the setup. So is the setup clear? Great. Now I can formulate my question, or our question, I should say, formally. Okay. The question is, for a pair of interim payoffs, little u and little v, that the sender might have, I'd like to know what I have to assume about these two guys in order to be able to conclude that increasing comparative statics holds between them, whatever the prior. In other words, regardless of the prior, I want it to be the case that the set of optimal distributions chosen when the sender's interim payoff is little u, that set is lower than the set chosen when the sender's interim payoff is v. That's the question. Now, as I mentioned earlier, more informative than is a strong notion. And so asking for increasing comparative statics is asking a lot. Okay? So I'm going to begin the enterprise by asking a weaker question. I'm first going to ask what it takes to obtain non-decreasing comparative statics. In other words, all I'm asking now is that u and v relate to each other in such a way that the set of optimal distributions under u is not strictly higher than under v. Okay. So if you think of these two sets as singletons, which again is fine, right? There's just one distribution here and one here. What I'd like is either for this distribution to be less informative than this distribution, that's fine. But I'm also allowing for the possibility that these two distributions are not ranked by informativeness. Neither is more informative than the other, okay, which means, loosely speaking, that these two distributions just provide information about different aspects of the state. Okay. So that's my question prime that I'm going to start with. And as I go on, please.
Question, if it's a good point to ask.
Yeah.
So I guess that there are multiple ways to consider more informativeness or less informative if you're talking about set of experiments, right? So that if it would have been singleton, then you get the usual standard Blackwell ranking. Why did you choose to work with this particular comparison rather than say all experiment in one set are more informative than the other? So I don't know if it makes your result stronger and weaker, but is there a reason to take this rather than other completion of the?
So there's certainly a reason, or reasons, I suppose. The other two, so you suggest a very strong notion of comparison of distributions that, for this set to be lower than this set, it had better be that every element of this set is lower than every element of this set. So we haven't actually done the exercise, but I think I know what I would have to tweak, and it would be a small thing in order to get results of that kind. So the fact that we haven't done that is kind of a convention, mostly from the comparative statics literature. I think we could do that without any difficulty. There is incidentally an in-between set order called the strong set order, which is in between the one I'm using and the one you suggested. And that's the one that's used most in the comparative statics literature, actually. And the reason we don't use that is actually because it turns out you can't get any comparative statics using that notion. Going into exactly why that's the case is pretty intricate. We might be able to do it in the questions. But since this weak set order I'm looking at here is economically just as good as the strong set order, that is something I believe very strongly. We feel like we've lucked out here. We have a more natural set order that gives us results, all the better. So we're not but I should, I'm flagging that is another natural notion that people use, and we toyed with it before realizing that it wouldn't work. Okay, so let me answer my first.
Ludvig,
sorry.
So before you go, can I ask a quick question?
Yeah.
So if there are multiple optimal signals, is it true that you can never rank them, or is it possible to have a case where you can rank them in the order of informativeness?
They could be rankable. So consider the case where the sender's interim payoff is just like just affine, like a long flat line. In that case, you're indifferent between all experiments. So so they can easily be comparable. Yeah. But it's not in an interesting way, I think, is kind of true in some sense. Yeah. You'd have to formally define interesting, I suppose, to make that rigorous. But okay. So let me ask. Let me answer my non-decreasing comparative statics question. Okay, the answer, as prefaced, is intuitive. It's about increased convexity, which feels like the right notion for capturing a greater appetite for providing information on the sender's part. Okay, the particular notion of increased convexity is one which we haven't seen elsewhere. Okay, if you've seen it, please tell us, because we'd love it if we didn't have to make it up ourselves. The notion is the following: I call one interim payoff of the sender coarsely less convex than another, exactly if the following is true. Okay, for any region of coarse convexity of U, by which I mean an interval xy, such that if I draw a chord from the point on the graph of U at x to the point on the graph of U at y, that chord lies pointwise above the function U. Okay. I call that a region of coarse convexity of U. Okay. Clearly, U doesn't have to be convex on this region, but in some coarse sense, it's convex on this region, or at least that's what I like to say. That's my definition. Now, what coarsely less convex then requires is that for any region of coarse convexity of U, like the one in this picture, that same region is also a region of coarse convexity of V. Okay. V lies pointwise below its corresponding chord on this region. There's one detail. The detail is that wherever U lies strictly below its chord, V had better also lie strictly below its own chord. That's the full definition. So this we feel is a natural notion of relative convexity. But like I said, it's one we haven't seen before, to our sorrow. So it seems necessary to say something about how it relates to conventional notions of relative convexity. The primary one of which is this one, which I think is due to Arrow and Pratt, or maybe de Breu. Okay, it's the one where U is called less convex than V, exactly if I can obtain V from U by applying a convex and strictly increasing transformation. In case U and V are twice continuously differentiable, this is equivalent by the Arrow-Pratt theorem to the Arrow-Pratt indices of U and V being ranked pointwise. Okay, the ratio of second to first derivative.
I'm so sorry, could you go a slide back just for, how do you call this definition?
Coarsely less convex.
Less convex. Thank you.
Yeah, coarsely less convex. We would have said less convex, but that was taken by this condition. Okay, so this condition is stronger than our notion of coarsely less convex than. And that's pretty easy to see, right? Suppose that U lies below its chord at a certain point, right? And that it's less convex than V in the conventional sense, okay? Well, then applying the strictly increasing function phi on either side of the inequality preserves the inequality. We get a V on the left-hand side, and on the right-hand side, we have a phi on the outside. If I bring the phi inside the convex combination using the convexity of the transformation phi, I obtain something even bigger, and voila, V lies below its chord as desired. Okay. So our notion, go on, sorry.
Is this the same condition as just like having more convexity for some envelope of the original function?
Our notion?
Yep. I take the convex envelope and I ask, when is the convex envelope of the function becoming more convex or less convex?
I don't think that's equivalent, but I'm not entirely sure. Gregorio, if you have a feeling about this, then you can conjecture as well as me.
Sorry, to be clear, you're asking whether the coarsely more convex is equivalent to
the envelope of one function being more convex in the traditional sense than the envelope of the other, the convex upper envelope. We can postpone this. Sorry.
Yeah, no, I'm not quite sure. I don't think it's equivalent. No.
I don't think it's equivalent either, but I don't have a pithy way of convincing you that it isn't. Yeah. So okay, that's a good question. Thank you. I wrote it down while Gregorio was talking. Thanks, Gregorio, and thanks, Philipp. Okay, so this is a notion, which is stronger than our notion. Okay, but here's another natural notion of comparative convexity. It's natural, and if you toy around with the persuasion models, comparative statics, you'll quickly arrive at this notion. It's natural to say that U is less convex than V if I can get V from U by adding a convex function. And that's pretty clearly sufficient for coarsely less convex than as well. So we can capture that too. And in fact, these two conditions are not comparable to each other. So one advantage of finding the correct notion of relative convexity, which I'm going to show you that the one I just defined is that it allows us to capture both of these very natural notions of increased convexity, which if we had picked one or the other, we would have lost the other one.
Can I ask another question?
Yeah, please.
So these sufficient conditions are great because they're easy to check. I'm just wondering if you feel like your notion of coarsely convex is an easy thing to check, because we have to do it for every XY pair. So.
Yeah. Do I think it's easy to check? Not in general. Another piece of homework for us is to see if we can come up with some nice sufficient condition that's strictly more general than condition A, which is nonetheless sufficient for coarsely less convex than. I imagine that there's some generalization. Although I don't know how simple it would be to check, it would be simpler to check. That would be very useful, I think. So that would be a nice thing for us to sit down and do. So, maybe you can index the function phi in some way, or I don't know exactly what it would be. But yeah, it's a great question. It's very, very natural. Yeah, just using the definition directly, it seems hard to check. Yeah.
So, but kind of for reasonable function where that changes their convexity finitely many times, I guess it's not hard to check in this case the relation between two given functions. You restrict yourself to those that change. Well, yeah, you need to
you
check.
still have to check a lot of intervals
regions as well, but
yeah, it's sort of some sort of in between kind of notion of the level of difficulty, perhaps. But certainly in kind of applied papers where people end up have a bunch of structure, their little u has some very special kind of shape, and in those cases it can happen that. So we have some example already of someone who wanted to apply our results, and they found that, oh yeah, actually I think they found that it was easy to see that coarse convexity ranking was not happening when their kind of the shift they were interested in occurred, and then they turned indeed comparative statics fails. So in sort of simple cases that might arise in applications, at least it can be easy to check. Okay, so that's the notion, and here's I should say that aside from sufficient conditions in the abstract, you can also ask for sufficient conditions on the sender-receiver primitives that would give rise to a coarse convexity shift of the sender's interim payoff derived from that microfoundation. Okay, that's another piece of homework for us. And now here's the theorem, which tells you that this notion of relative convexity is the appropriate notion which characterizes non-decreasing comparative statics. Okay. So it says that for a pair of upper semi-continuous interim payoffs that the sender might have, the following two things are equivalent. On the one hand, the payoff little u is coarsely less convex than the payoff little v. And on the other hand, non-decreasing comparative statics holds between u and v, whatever the prior. So regardless of the prior, it is not the case that more information strictly is provided under u than under v, precisely if u is coarsely less convex than v. Okay. So I'll give you some idea of why this is true. Okay. The necessity of coarse convexity ranking for non-decreasing comparative statics is straightforward. Okay. Because if u is not coarsely less convex than v, that means that we can find a chord where u lies pointwise below its chord. But if you draw a chord in the same place for v, v goes above its chord in the interval. Okay. Well, in that case, you can find a prior that's concentrated on this chord where u is below its chord, which means it likes to spread out probability mass. So it likes to provide a lot of information. Whereas v likes to stay on this region that's above its chord, meaning it prefers not to provide information. Okay, so v provides strictly less information than u. Okay, that's the proof. There's not much more to it than that. You can do it in 3 lines. So the non-trivial part of this result is the sufficiency argument. And it goes like this. Okay, there are 2 steps. I'll tell you the steps, and then I'll tell you why the steps are true. Okay. The first step is to deduce from u being coarsely less convex than v that the functional big U, which is the sender's expected payoff as a function of her choice, her distribution, this linear functional, that function is interval dominated by the corresponding functional when her interim payoff is little v. Now here, interval dominated here is a generalization of single crossing dominated, as is familiar from the monotone comparative statics literature. Okay, that's step 1. Step 2 is to deduce from this interval dominance ranking the non-decreasing comparative statics conclusion that we were looking for. So that's the structure of the argument. And now I'll tell you why these 2 steps, how these 2 steps are established. Okay. The second step is nice because the second step can be obtained by just taking a theorem off the shelf. Okay. The fact that interval dominance ranking implies non-decreasing comparative statics is a theorem that's due to Jonquois and Bruno Strudovisi. So we think this is great. we're very happy that we're able to make some use of the wisdom of the monotone comparative statics literature in proving some comparative statics results. Okay, so we think this is great. Okay. Unfortunately for us, there's the first step to establish as well, and we haven't been able to find a very simple proof of that. Okay, so sadly, there's still some work involved in proving this theorem, albeit it's not like very interesting work, I think. And that's the sort of gist. If that's clear enough, then I'll move on to the next section. Okay. So we're halfway to the question that we're actually after now. Now, theorem 1 tells us that if we want increasing comparative statics, then it's necessary that the sender's payoff become coarsely more convex. Okay. But it's not sufficient, which is why we're only halfway there. Now, you may very well ask, what can go wrong? Okay, so how could it be that a coarse convexity increase could fail to lead the sender to provide more information? Okay. And that is an interesting question. And I hope to have a little bit of time at the end to show you graphically what can go wrong. But for now, I'm going to concern myself with a question of what has to be assumed in order to rule out this pathology. I call it a pathology, but it can very easily happen. Okay, so I need to assume something pretty strong, such that convexity increases of the sender's interim payoff do in fact suffice for increasing comparative statics. Okay, that's the remaining task. Now, for the remainder, I'm going to restrict attention to well-behaved interim payoffs of the sender, meaning the following, okay? We're going to be looking at interim payoffs which are continuous and which have a derivative. And that derivative should be continuous and bounded. Okay? And furthermore, I'm going to want interim payoffs which whose curvature doesn't switch infinitely often. Okay, by which I mean, this is the kind of functions that Itai was referring to earlier. Okay, I'm going to be looking at functions where I can partition their domain into finitely many pieces, on each of which the function is either concave, strictly concave, or strictly convex, or affine. So, this is mostly sort of technical boredom. I think almost all these assumptions are harmless. Okay, the only one that I dislike, and I think Gregorio feels the same, is the assumption of continuity. Okay, the first one, because if this little u is coming from a receiver taking actions as its microfoundation, then we would expect whenever the receiver switches actions at a belief, typically for the sender's payoff to jump, actually. Now, you can approximate that with continuous and steep, okay? So I think in the end, it doesn't matter very much, but it would be nice if we could obtain our subsequent theorem that I'm going to show you without this continuity assumption, but we haven't done it yet. Maybe we never will. We shall see. Okay, now here is the property that we're looking for, the property that's going to close the gap between non-decreasing and increasing comparative statics. I'll warn you before defining it that it's a curious property. Okay, we call it the crater property for lack of a better name. It goes like this: a regular interim payoff satisfies the crater property if, for any region on which this interim payoff is first concave and then strictly convex and then concave again, the following is the case. If I draw tangents to the function at the endpoints of this region that I'm considering, those tangents are not parallel, but rather they cross exactly once. That crossing occurs in the strictly convex region of the function. And this last bit is the important bit, the crossing occurs below the graph of U. So for any concave, strictly convex concave bit, if I draw tangents at the endpoints, they cross once in the strictly convex region and, crucially, below the graph of U. So in the picture here, the property is satisfied, evidently. Okay. But it's very easy to draw pictures where it's violated, like this picture here. Okay. So if the walls of the crater are too flat relative to how wide and shallow the crater is, then the property is going to be violated. That's the crater property. It's curious, which doesn't necessarily bother us too much since it turns out to be the right notion. It's necessary and sufficient. Okay. Nonetheless, we should think a bit about how strong it is. And I think the bottom line is that it's strong. Okay. However, it's not a trivial property. Okay. I just showed you a picture where it's satisfied by a function that doesn't seem unreasonable. Here are some other examples. S-shaped functions satisfy the crater property as previously advertised. An S-shaped function is one which is concave and then strictly convex, or vice versa, strictly convex and then concave. Why? Well, it satisfies the property vacuously. Right? An S-shaped function just doesn't have any concave, strictly convex, concave regions. So the crater property demands nothing of an S-shaped function. And the reason I'm interested in S-shaped functions is not just because they satisfy the property, but because they appear a lot in the persuasion literature. Okay, so it turns out that S-shapes are tractable also for characterization exercises, not just for comparative statics exercises. This is something that's known by people before us. And another shape that also vacuously satisfies the crater property is the W shape, strictly convex, concave, strictly convex. So those are some sufficient conditions which seem non-trivial. Okay, they're nowhere near necessary. Okay. There's, in fact, the crater property doesn't place any restriction on how many times the second derivative changes sign. So there are loads of shapes that satisfy the crater property. I'm going to give you a necessary condition as well. And this one is for the fans. Okay, this is a necessary condition that follows from some work actually by Itai and Philipp, as it happens. Okay, so a necessary condition for the crater property is that whatever the prior, there is at least one signal which is optimal of the monotone partitional form. Okay, so why that's true? Well, it follows from results in these two papers, together with inspecting the crater property. And I'd rather not get bogged down in defining monotone partitional for anyone who isn't familiar with the term, but I apologize for that. This is sort of inside baseball.
So what I wanted to ask about the definition of the crater property. So it only needs to hold for those parts who comes consecutively, right? If they are far apart, and this is, I find, a little bit strange. So if there are far apart regions which are both concave, and then the functions can go crazy in the middle and changes, then still, as long as it holds for consecutive, only for these regions that comes one after the other, it's enough for you. True? Yeah.
So indeed, I mean, I agree with you. That is the sort of non-trivial. The fact that this property is sufficient is non-trivial, basically for the reason that you'd expect maybe, at least we, I think, expected early on that there would be some sort of big global property that would need to be satisfied to rule out pathologies. And it turns out, however, that if there is a pathology, a violation of increasing comparative statics, then there must in fact be a pathology on a region, a local region of the concave, strictly convex, concave variety that looks, the picture has to look like this. So of course there could be violations of other sorts if you like, but there is always going to be a violation that has this kind of picture. That's sort of essentially what we prove in the sufficiency part. And I agree that it's not obvious at all. But the fact that the condition is local is we think, an advantage. It feels much simpler and sort of more geometric than something global. Thanks for the question. Okay, so yet again, there's homework here. So there's various things, but one of the things is to think of what sufficient conditions on the primitives of the sender-receiver microfoundation might be in order to obtain the crater property. So for example, what does the W shape mean in the context of a sender-receiver story with some additional structure perhaps, okay? That's something seems straightforward enough, but we just haven't done it yet. So that's going to be in the paper eventually, something like that. Okay. And now here's the theorem, the main theorem, I suppose. It says the following: for a regular interim payoff little u that the sender might have, the following two things are equivalent. So on the one hand, this is an interim payoff which satisfies the crater property. And on the other hand, it holds that for any coarsely more convex interim payoff that the sender could have, for any coarse convexity increase, we have increasing comparative statics, whatever the prior, okay, assuming it's atomless with convex support. So let me say it again, okay. For a regular interim payoff that the sender might have, okay, if it satisfies the crater property, then every coarse convexity increase of this interim payoff is going to lead to more information being provided optimally by the sender, regardless of the prior. Okay. And conversely, if the crater property is violated, then I can find some coarse convexity increase and some prior for which informativeness of optimal signals does not increase. Okay. It goes sideways. We get neither more nor less informative choices.
Quick question.
Please.
If U satisfies the crater property and V is coarsely more convex, does it imply something about V satisfying the crater property?
No. No, it doesn't. We at some point we thought maybe that was true, but then it's not true at all. Actually, there are loads of counterexamples. Yeah, so it's not the case actually.
Okay.
So it's a good question though. It would be natural and useful perhaps. Okay. So that's the theorem. So let me talk about why it's true. The sufficiency part is the harder part once again, and it goes. All I have to say about it is the following. First of all, the argument is bespoke in the sense that we do not take results off the shelf, but rather come up with an argument of our own using the special structure of the persuasion problem. Okay. In particular, the proof takes place in the dual. So the persuasion problem is a linear program, and the dual, which was sort of looking at the dual, was something that was first done in this paper. The dual turns out to be a space that's very useful for obtaining comparative statics. So that's the space in which we work. The main thing I want to say about the sufficiency proof, though, is that indeed, I want to say something about what it isn't. Okay, what it isn't is an application of the theory of monotone comparative statics, and there's a sort of profound reason for that. Okay, the reason is because every monotone comparative statics theorem, general purpose, like the Milgram-Shannon theorem, the Quastrulo-Visi theorem, in order to get increasing comparative statics, they require that the decision maker's payoff as a function of her action, so that's this functional big U, is supermodular in some suitably generalized sense. Okay, there's always an assumption like that in those theorems. And in our setting of persuasion, that's a crazy strong assumption. Okay. Even the weakest of these notions, which is called integral quasi-supermodularity, long name, boils down to the requirement that the sender's interim payoff is either concave or convex. So I think even strictly concave or strictly convex. I think this here is not exact. It's not entirely precise. Okay, which is a crazy strong assumption. Concavity obviously means that no information provision is optimal. Convexity obviously implies that full information provision is optimal. So only these two trivial polar cases can be handled by the theory of monotone comparative statics. Okay. So we have to go our own way. So in the remaining time, I'd like to give an idea of why the crater property is necessary. Okay. I have something like what? When do we start exactly? Do I have like 8 minutes, 9 minutes?
Sorry, yes, approximately 7 or 8. Yeah.
Great, thanks. Okay. So what I want to convince you of is the following. Right? Suppose that we have an interim payoff little u of the sender, which violates the crater property. So I can draw tangents at some points x and w like this, such that those two tangents cross above the graph of the function u, as in this picture here. By the way, it's going to be useful to consider the pointwise maximum of these two tangents. That's this affine, piecewise affine and convex function p that I've drawn here. Okay. What I want to show is that for a u that violates the crater property, like in this picture, I can find a prior, which is atomless with convex support, and a regular and coarsely more convex interim payoff v, such that increasing comparative statics fails. Right? That's the goal. That's the necessity proof. Okay. And here they are. Okay. The prior I'm going to construct as follows. It's going to be atomless. It's going to have support in the picture, just so that I don't have to worry about what's outside the picture. The mean of the prior is going to be big X, the crossing point of the tangents, or the kink point of P. Okay. And the conditional means are going to be the tangency points. Okay. So the mean of the state, conditional on its lying below the kink point big X, is the tangency point little x here. Okay. And symmetrically, the mean of the state conditional on the state being greater than big X is the tangency point W. That's the prior. The alternative interim payoff V is going to be like this. It's going to coincide with U to the right of the kink point X. And to the left of the kink point big X, it's going to be strictly convex and pointwise above U. Okay. This is clearly coarsely more convex. In fact, modulo some boundedness of slopes issue, this is just adding a convex function, in fact. Okay. So in order to convince you that increasing comparative statics fails, I'm going to have to consider information provision incentives under the payoff U and under the payoff V, and then argue that they are not ranked by informativeness. Okay. So let's start with V. Okay, V, by inspection, is S-shaped. Right? It's strictly convex, and then it's concave. So that means that we can take a result off the shelf, which is something we like to do. Okay. Anton characterized optimal information provision when little u is S-shaped, or little v in this case is S-shaped. Okay. And he showed that there is an optimal distribution that looks like the following. Okay. It's called upper censorship. Okay. The interpretation in terms of signals is the following. There's a threshold, little a. Okay. If the state turns out to be lower than this threshold A, then the message which is sent is the signal is such and such, fully revealed the state. Whereas if the state realizes above the threshold A, the message that's sent is simply the state is above A, I will say no more. So full concealment or censorship. Okay. So the distribution is it hugs the on the full revealing region, the distribution hugs the prior, and then above A, all the probability mass is concentrated at a single point B. Following the message, the state lies above A. The posterior mean is just the mean of the state conditional on the state being above A, which I've called B here. Now that's upper censorship. the optimal choice of the threshold A is characterized as follows. The optimal A is such that the implied conditional mean B, if I draw a tangent to V at the conditional mean, it cuts the function V again at the threshold A. Okay. This is Anton's result from his job market paper, I think. Okay, given the time, I'm not going to prove it. Okay, I'm going to take it on faith. You may or may not be familiar with it. Okay, what I want to highlight is that, you know, it's a geometric fact. Sorry, go on.
I kind of, so I can see how you basically can have a lot of lines tangent to the let's say increasing bit of a functions, right?
Mm-hmm.
So you can move the A up and down. It has to be to the left of X,
Mm-hmm.
right?
Mm-hmm.
But I could construct something which is slightly closer to X. The tangent would, you know, I can find a tangent on the B would be to the left of what it is right now. So why is this particular A better and not the one I just described? I'm not sure what narrows down exactly what A is, basically. You said it, but I didn't get it.
I mean, I didn't say why this is the optimality condition.
Yeah.
If you're asking whether A is uniquely determined by this tangency condition, the answer is yes. B is not uniquely determined. If there was a flat region here, like an affine region here, in principle, there could be many B's, but there's still just a single A. You know, there's two systems of equations. There's this equation, there's this system here.
Yeah.
And then there's, and I mean, this is an atomless distribution as well, remember?
Yeah.
And then the other, yeah, so I mean, that's not right.
Okay, so I guess I'm missing the other equation, I suppose.
Yeah, so I didn't write down the other equation. I think
okay. Fair enough.
But I'll skip why this is optimal in the interest of time.
Okay.
Luckily, Anton did it for us, so it's at least published. Okay. So let's return then to U. Okay, sorry, I've had to say something about V. Sorry. What I had to say about V is, as you just pointed out, A has to be strictly lower than big X, which means that under this distribution, there are states strictly to the left of big X, the tangent, the kink point, which are pooled together with states to the right of big X, right? There's a big old message that's sent whenever the state is above A that says the state is above A, and I will say no more. Okay, so states on either side of big X are being pooled together. Okay. Now, what I want to show in the remainder, quickly, is that under the coarsely less convex interim payoff U, pooling states on either side of big X together is strictly suboptimal. If I do that, I'm done, because in that case, there's some pooling that's going on under V, the coarsely more convex interim payoff, and that same pooling is not going to happen under U, which means that it's not true that uniformly more information is being provided under V optimally. Now, the reason why this is the case is the following. Okay, it is optimal under U to do instead the following thing. Okay, it's optimal to use the distribution, which I'll call big G, which has just 2 points of support. Okay, this is the distribution, the signal, which just only reveals whether the state is below big X or above big X and nothing else. Okay, so when the message the state is below big X is revealed, the posterior mean is just the mean of the prior conditional on the state being below big X, which, remember, by construction of the prior is little x. And symmetrically, the other message leads to the posterior mean W. So the support of this distribution is just these 2 points. And the mean is the prior mean, big X, by feasibility. Okay. I claim that this is optimal. And clearly, this doesn't pool together states on either side of big X. Okay. Now, the way I show that that's optimal, this is the last thing I'm going to do, is by a chain of inequalities, because I don't know how else to do it. Take any other distribution H that's feasible. That's a mean preserving contraction of the prior. I'm going to show that it's worse. Okay. How good is this distribution G? Well, it's the integral of U with respect to G. That's the same as the integral of p with respect to g, this function p here. Why? Well, these two functions are not the same function, but on the support of g, they coincide. The support of g is just 2 points, x and w, and by inspection, u and p coincide at those points. Step one. Step two, if I replace the distribution g with a prior, which is a mean preserving spread by feasibility of the prior, that also doesn't change the value of the integral. Why? Because this amounts to spreading out probability mass from x to the rest of this interval here to the left of big X, which doesn't change the value of the integral since p is affine here. And similarly, spreading out the probability mass concentrated at w to the whole of this interval to the left of big X, also affine, so also doesn't change the value of the integral. So we have an equality here. Okay, and step three, suppose I now replace the prior with the mean preserving contraction h, right? This is a feasible distribution. It's a mean preserving contraction. That's going to give me a smaller integral because I'm integrating a convex function. Okay. Last step, suppose I now replace the convex function p with the function u again. That gives me a smaller integral because p lies pointwise above u. That's the proof of optimality. The one piece that's missing is just that if I were considering an alternative distribution h, which did pool states on either side of big X together, then this first inequality here, using convexity, would be strict. So that would be strictly worse. That's the argument.
Just I lost something. Don't you need that these two conditions of the other function and this hold simultaneously? So isn't it the case that you need a to give us a distribution that both has the properties that the conditional expectation above X is W and below X is X, and has the point at which the tangent starts is to the left of X in the other function? No? So I thought
the other function was chosen as well, right? So the argument started just with the function u, and then I was allowed to choose the distribution and the function v.
So you choose it after you construct the distribution for p. So you first, in order to prove it, you first look at this one, choose the distribution you have just constructed, and then choose the other function v. Unless I'm missing something.
That's right. Yeah, I choose them in this order. Yeah, thanks for the question. Okay, I should wrap up because I think I'm a little over time, for which I apologize. I'll do that like this. Thank you. We can talk about the rest in the questions, perhaps.
Can I ask a kind of a clarification before I open the floor? Because so the proof, the reason you need, if we can just go back a couple of slides to the last picture, this one exactly. So the point here is if this dashed line was below crossed the thick line at some point, then this chain of inequalities, because you're using the fact that p is everywhere above you, it's
this last step would be invalid.
Okay, now, but it doesn't have to be. So my point is, does it have to be pointwise above? Is it because if it isn't pointwise, I can always find another example, not this one that you're using, such that?
Yeah.
Or I mean, or is it that on average? I mean, so clearly the answer is it has to be pointwise because otherwise the theorem would change. But that's it, right? If it wasn't pointwise, then it would be something else that you couldn't construct.
Yeah. So if the Crater property is violated, then there is a picture like this, and then I can apply this proof. And in fact, if there is no violation of the Crater property, so I can't draw any pictures like this, then it turns out that's the sufficiency proof. I can't draw any other bad pictures either, but that's not obvious at all. That's the harder part. that can't be sketched so easily as the way I just
Okay.
answered that question.
So Philipp or Itai, whichever one of you wants to get started, if you have any other comments, questions, or things like that, please.
I mean, maybe I could ask a question. I don't know how interesting it is, but like you made a comment which I thought was very interesting. You talked about supermodularity and monotone comparative statics, and how this methodology is in some sense different. And I couldn't completely follow, because in some sense, for supermodularity, it depends on with respect to which order you define it.
Yeah.
And I just like I couldn't follow that step, and I would be very curious if you could repeat it.
Yes. In fact, I think this is the point. So there's a point about it here that I can show you at the same time. So it's not exactly, doesn't answer your question per se, but it's better to have it up. So indeed, quasi-supermodularity depends on the order. The order here, though, is given. The order is less informative than, and the objects in question are the distributions. So when I'm talking about quasi-supermodularity of the objective function of the sender, which I guess I should show you, this object, right? The expected payoff of the sender is a function of her action, the distribution. When I'm talking about quasi-supermodularity or some generalization of this payoff, I mean the quasi-supermodularity notion obtained from the less informative than order on the space of distributions. And that's the sort of answer in the context of this model. But I think what I had in mind, I guess what was on my mind, and maybe what's also on your mind, is what some of this might mean for monotone comparative statics and more general problems. And that's something we're very interested in. The reason being that, as I highlighted here, if you wanted comparative statics from the abstract general theory of monotone comparative statics, you would have to assume some kind of quasi-supermodularity, whatever the underlying order happens to be. And that, I mean, actually, in my experience at least, is a very limiting assumption, because actually, if you check in applications whether quasi-supermodularity holds, it never holds. It's really hard to come up with examples in which it holds, actually. At least that's been my experience. I spent an entire year as a research assistant when I was a grad student helping write a book on monotone comparative statics, and I really struggled to find examples of applicability. So this is like the biggest weakness, I think, of that literature, of the monotone comparative statics literature. And we found here in one particular model a way around it. And we managed to obtain comparative statics in the increasing sense without it. And it's we have some other condition which is stringent but not trivial. And so this raises the question of whether there's some abstract structure that could be extracted from our technique, our proof technique, that would allow you to obtain some useful comparative statics theorem with more general applicability. And we really don't know, but we want to find out.
Very interesting. Thank you.
Thanks.
Hi.
Just one comment about the creator property. Indeed, so when I wrote the paper with Yaakov Takuro and Ran, we play around a lot with trying to find optimal price function or optimal policy for examples, for practical, and finding optimal signals. It turns out to be highly non-local property, highly non-local, something that global. You need to look at the entire function. And this is why I was surprised that you have a kind of local property for this characterization, which is nice.
Thanks. I agree that that's sort of a slightly more hidden virtue of this theorem, because ultimately the sufficiency proof is all about that. Actually, it's all about exactly. I guess I said it before. It's all about looking at this. When a pathology arises, it could have some. There could be in some way that depends on the whole function in a very global way. But it turns out that you can show that then there must also be a local pathology. It's not obvious. It will be, I mean, I think, we might sort of refine the proof over the years, sort of to stage by stage. I hope to be able to get some sort of reasonably brief way of expressing why that is the case, actually. But at the moment, I don't have it. The proof is pretty long, and I can't distill it down into anything short. Thanks for the question.
Okay, so anybody else who might have questions? I have one, but I'm happy to defer to other people before I ask mine. No, nobody? Okay. Ludvig, this is an extremely long shot. I'm probably gonna embarrass myself, but the shape of these crater function reminds me of something called the bathtub shape that sometimes people use for hazard rates and so on and so forth. But it's really different because that's for hazard rates, and it is about decreasing flat and then increasing or the reverse, basically, things like that. But this literature on survival rates and so on often looks at these things. There's a relationship between the underlying shape of a distribution and whether the hazard rate is bathtub or reverse bathtub or stuff like that.
Oh no,
I don't know if you ever seen this stuff, but yeah.
No, but we'll look. It's funny actually because the other name we had for the crater property was the bathtub property because it looks like a bathtub, right?
Yeah.
But we thought it was too silly.
Yours is a much more restrictive because it needs to be concave, convex, and so on. Yeah. This one is just decreasing and so on. But yeah, so there are paper. I mean, it's I suppose an engineer who does these things would know this like the back of their hand. They know that if you have a certain type of concavity, convexity in the distribution, then the hazard rate has this particular property and so on.
Oh, but that's great. Thank you.
Yeah. Does anybody else have any comments, anything to say?
Just a small comment about the notion of more convex or more. So indeed, I never came across ranking of functions according to their convexity, but I think I saw. I'm almost sure I saw a ranking of sets. So and you can always think of a function by looking at the epigraph, the set of points above it as a set. So I wonder if some such notions coincide, the set notions of more convex, of ranking convexity coincide on your notion, or if you can somehow define this notion over subsets rather than graphs and then apply to function. I think it may be more natural to some people, not all. But,
that's a great idea. That sounds like it might be quite fruitful, actually. We haven't thought about that, but it's very natural. I agree. Thanks for the suggestion.
Okay, I've just looked at the time. I think we can stop the recording, and then maybe final comments, questions, and say goodbye until next